my name's Andrew Newdigate. I'm in the infrastructure group at GitLab, and most of what I do there is focus on GitLab.com and try to keep it up and running. So this talk is about capacity planning, and the reason we started thinking about capacity planning was to avoid resource saturation. So I guess the question is, what is resource saturation? And probably the best way to illustrate this is by walking through an incident that we experienced on GitLab.com, which was caused by resource saturation. And in actual fact, it was one of several incidents that we saw that happened within a short period of time, and they were all related to saturation problems. And this led us to start thinking about this problem in a little bit more detail. So it all started with this graph. Just by the way, I think it would be really useful if we could get animated GIFs in Grafana. I don't know if Tom's here, but it would be a super useful type of annotation. So this is the apdex score of our web service. So it measures the percentage of requests that complete within a satisfactory amount of time. So with apdex scores, high is better. And the red line, like right near the top, is our SLO for that metric. And so when the metric goes below the red line, we start getting alerted. And so what you can see is that our latencies like rapidly shot up and our apdex tumbled, and we started getting alerted a lot. What we started seeing was major slowdowns on our web endpoint. We started seeing similar slowdowns on our API fleet. Our background processing started getting really bad, and we were getting a lot of notifications and pages. So we narrowed the problem down to our Redis caching fleet. Now, some of you may know, Redis is a single-threaded server, and this means that it can only scale vertically on a single core on a single machine, and that's as much capacity as you can get from a single Redis instance. And so our Redis cache runs on Google Cloud instances on N1 standard 4 machines, and these have got 4 cores, but Redis can only use one of those cores. So the average CPU on the machine was actually pretty low, but somewhere around 30%, but Redis was pinned at 100% basically on one of those cores. So we needed to figure out why this Redis instance had suddenly started acting up and causing us so many problems. And so we went through the checklist of all the usual suspects that cause these kind of problems. And obviously, the first one that we always look at is, was it an application change? Had some bad piece of code been deployed and was now hurting us? And it didn't seem that way. And the second thing was, had we changed our infrastructure? And again, everything had been the same for ages. And then we always also look at, is it a user doing something bad? Is there like a bad actor trying to mine Bitcoin on GitLab? Something like that. And it didn't seem to be that way either. But something had clearly changed, because the day before, everything had been so good. And now we were seeing everything spiking up across our application. But it didn't seem to be related to any of the usual causes. So it was only when we took a look at the data for Redis CPU over a much longer period did we realize what the problem was. So this graph shows Redis CPU utilization over a 3-month period, so quite a long period of time. And the thick yellow line is the CPU utilization metric, and the thin dotted red line is like a trend, a 7-day rolling average trend over time. And so gradually, our Redis CPU had been going up, had been trending up week on week, but just quietly and not to any major effect. And then, in fact, in the previous week, it had only been fractionally lower, just a tiny bit lower, but yet we'd experienced no problems at all in the fleet. And there was only once we hit complete saturation, which is the circle on the right, that everything completely failed horribly, and all of our servers started really struggling. And we obviously passed some sort of tipping point. And beyond that tipping point, everything started failing horribly. But until that moment, everything seemed to be going fine. So obviously, if you've run out of CPU, the obvious fix is to just get more CPU, right? And so the first thing we looked at was like, what CPUs is Redis running on? And we were actually running it on Intel Haswell processors. And GCP offer newer Skylake processors. So like, woo, we can fix the problem really quickly. We'll just change the instance. But we did some benchmarking, and we realized that for our workloads, the newer processors were absolutely no better. They had the same performance as the older Haswell processors. So there were several application changes that we could make to sort this out. One would be to shard Redis at application level. Another would be to switch to Redis cluster, which is a sort of sharded Redis equivalent. And both of these would give us horizontal scaling in our Redis cluster. But of course, these are both pretty big changes, and you can't just do them in 5 minutes. And they required major application changes. And this isn't ideal when you're experiencing major latency issues and you're getting paged every few minutes. So in the end, we managed to fix the problem by addressing several old inefficient caching endpoints and just reducing the load and getting us under the tipping point. And then we could address the problem through other fixes as well. But we resolved the problem, but really what we wanted to do was to make sure that we avoided this kind of saturation issue in future. We didn't run into it again. So what were the main lessons that we learned from this incident? Well, the first was that while our symptom-based alerting had worked really well, it only notified us of the problem when it was too late. So once we got ourselves into a bit of a corner. And then had we had more warning, we could have addressed the issue beforehand, before the incident occurred and possibly avoided it altogether. The second thing we learned was that unlike incidents resulting from changes in the application or in the infrastructure, resource saturation issues can be much harder to resolve. We couldn't just revert to change or block a problematic user in our infrastructure. And they're very often related to increased traffic volumes. And so unless you can tell your users to just stop using your system, there's often no easy workaround. So another thing that we kind of learned from this whole incident and from the other similar incidents was that failure is very much not a linear thing. When your application is running just underneath the tipping point, you could look at the latencies and your error rates and everything appears to be totally fine. And then request traffic volume increases just slightly and you pass the tipping point and then everything starts failing horribly everywhere. And in some cases, in the worst cases, adjacent services go under more pressure and you get this cascading effect and you could have your whole application fail. So we started thinking about how we could build some sort of tooling that could help us plan ahead and spot these sort of trends before they became a problem. And of course, we use Prometheus for all of our monitoring. And so it seemed like a logical place to try and build this. So with this in mind, we set about the goal of building an early warning system that would help us predict and avoid saturation issues before they became a problem. Here are some of the goals that we wanted from the system. So the first thing, we wanted to build a normalized metric for all resource saturation in our system. So we could analyze and compare saturations throughout the entire application. And then we wanted to measure as many different saturation points as we could. And then we wanted to use this data to predict future saturation problems before, and so we could be forewarned of problems. So the way we measure saturation in Prometheus is pretty simple. We just build a gauge metric, and we calculate this really simply as the current utilization of any resource divided by the maximum possible usage for that resource. And this gives us a measurement on a scale between 0 and 1. 0 is totally underutilized, and 1 is totally at capacity, and you've got no spare capacity anymore. So really what we're trying to avoid is for resources hitting 1. And so for each service, we want to track multiple saturation metrics. So in our definition, so a few people have actually spoken about services today already. We just have a service label that we apply to groups of similar instances. So, all of our Git storage is one service, all of our web storage is another. So what we wanted to do was we wanted to record saturation metrics at the service level. So we could say this disk utilization on the Git storage service is saturated. And so we wanted to aggregate up to there. So if you have 10 instances running a service, we don't track the individual saturation metrics on each instance. We just roll it up to the service level. And the second label that we apply to all of our metrics is a component label. And this describes the name of the resource that we're measuring. So that could be memory or CPU or database connection pools or whatever the resource is that we're monitoring. So it's probably quite, will make a bit more sense if I describe an actual example of this. And so a fairly straightforward example is file descriptors. So in one of the earlier talks, someone spoke about running out of file descriptors. So that's another classic resource utilization problem. And so each process in a system has got a limited number of file descriptors. And if you run out, then your application will start failing in really horrible ways. So by default, the Prometheus client, at least the Golang Prometheus client, will record this number as process OpenFDs and process MaxFDs, respectively. So if we plug these into our formula, we just get a super simple, we just divide the one by the other, and we get our saturation metric. So if we plot that, we get a graph that looks something like that. And that shows saturation ratios for each application instance in our application. But the problem here is that there's just way too much data. On this graph, there's 2,000 different series, and that's too much. And so what we want to do is aggregate that up to the service level. And so we aggregate up with to the worst case for each service. And this is a really important distinction about what we're doing here, because it's always the worst case that is the thing that's going to cause the bottleneck. So often with ratios, you tend to use average as your aggregator. But with saturation metrics, you always use the worst case. And that's because if you have like one process that reaches the file descriptor limit, it could degrade your entire application. It's not the average that matters, it's the maximum. And so you'll see max get used a lot with these kind of recording rules. So if we plot that query again with the max aggregation, we get a much more manageable amount of data. We have one series per service. Instead of one series per instance. And it's also much easier now to understand what's going on with our application. So if we take this and plug it into the recording rule that we were talking about earlier, we get a PromQL query that looks something like this. And it's got two dimensions. It's got service, which is exposed by the PromQL, and then we add a second static label called OpenFDs to say that this is for monitoring the file descriptors resource. And with this, any instance that has the process OpenFDs and process MaxFDs on it will automatically start getting tracked with this. I'm just going to run through two more quick examples. So going back to the Redis CPU saturation that I spoke about earlier, this is how we'd model that with this system. So we use metrics exported by the Redis exporter, and we sum the user time and the system time for the process. And we know that when this reaches 1, which is to say Redis is using 1 second of CPU per second, then we know that Redis is at 100%, and that's what we want to avoid. And again, we aggregate this up to the service level because there could be multiple replicas within a service, but we only care about the worst case. And so for our application, we get different Redis services, and you can see the example at the bottom there. We've got 2 Redis services, and they each have a Redis CPU label on them. And then just one more example. This is Postgres connections. It's like, how many connections are you using out of the configured maximum for Postgres? So if we ran out of Postgres connections, we would hopefully get warning of that with this. So we use this approach on many other resource limits inside our application. On GitLab.com, we're currently tracking over 20 different resource metrics for our services. And we're adding more all the time. So whenever we hit some sort of saturation limit, we plug it in, we create a new recording rule. And I think there's about 250 different combinations of services and metrics that we're recording. So there's quite a lot of different data that we're adding to this. So once we've got all these saturation metrics in the same format, we can do some basic alerting on this. And this can be done with a very simple, I think Simon would agree, very simple alerting rule, because he was saying it's good to have simple rules. And what this says is that if any saturation ratio in your system, so any service resource combination is greater than 95% for more than 5 minutes, send out an alert, and you can include the labels in the alert. We actually send it to PagerDuty, and we've got this second little thing that we call Slackline that takes the alerts and turns it into like quite a big Slack message. And it includes embedded Grafana graphs. And then on the thread for the alerts, it includes where to go for runbooks and links to Prometheus and a whole bunch of stuff. And then also when the alert is resolved, we send another graph that gives us the final sort of charts showing the resource returning back down. So that's quite a useful little thing that we've built. But of course, like what we really want to do here is avoid resource saturation altogether rather than getting alerts on it, because we know that by the time we've hit that saturation, we add capacity, and that's the whole point of what we're trying to avoid. So what we want is some forewarning, maybe like a few weeks if we could, that'll let us know that something is starting to become serious and we need to take a look at it urgently. And so now that we've normalized all of our now that we've normalized all of our saturation metrics into a single form, let's take a look at how we can use this data to do some sort of forecasting. So the first thing we tried was linear interpolation, but this didn't really work very well. The problem is with linear interpolation is that we're not really dealing with linear data, and so the data's all over the show, and we get very misleading results. So this is just a plot of if we were to use linear interpolation and compare that to the actual value, that's what we'd see. So the blue line is the actual value, and the red line is what we would have linear interpolated 7 days before. So that's a terrible forecast. So we started thinking, like, we didn't really know if this was going to be possible in Prometheus, and maybe it didn't have the right expressive powers. And we were a little bit stumped, and we went back to the drawing board. And then we were struck by an idea that instead of trying to have a weather forecast and predict a perfect value for what this metric is going to be, all we really need is the worst case scenario, right? So we don't need a weather forecast. We just need we need a hurricane warning. We need to know when bad things are going to happen. Not, next week this is going to be at 50% saturation. We just need, hey, this thing is soon going to run out, and you need to do something about it. So if we just focus on the hurricane warning part and not trying to come up with like a full prediction, we can build up a solution that exclusively uses PromQL. And the way that we do this is we linear interpolate on the trend in the data. So if the trend is going upwards, we can linear interpolate on that. And then we add the standard deviation, which gives us an idea of how much variance there is or how much volatility there is in that metric. And we basically add those together, and it gives us like a worst case scenario. So we can project that forward. We can say in 2 weeks' time, the trend's going to be there. The variance is like this. So these are the things that we really need to look at first. And this gives us our worst case. So I'm going to skip through this pretty quickly, but we've got 3 recording rules that we use to do this. The first one gives us our 1 week trend. The second one gives us our standard deviation over a 1 week period. And then what we do is we take those and we plug them into a third recording rule, which gives us our linear prediction on the trend for 2 weeks, or for 14 days. And so we use those 3 things, and at the end of that, we get a Grafana dashboard using that data. And earlier, Adam was talking about Grafana, and we actually use Grafana to publish all of these dashboards, and highly recommend using it. But because this data isn't particularly accurate, we don't do sort of time series on it or anything like that. We just show a table of where we might see potential saturation. So we've got 3 sections. The first section is resources that are actually over their SLO at the moment. So in the previous thing, I said that we use a 95% SLO, but we actually have different SLOs for different metrics. It's just a small extension. And then the middle section shows us things that are currently at risk of becoming saturated using the standard deviation and their current value. And then finally, the bottom section shows us things that are based on the current growth and the volatility that we see in that metric, things that are probably going to become, or possibly going to become saturated in the next few weeks. So what's important to note is we don't use this for alerting. Like, nobody gets woken up at 3 a.m. to be told that a Redis machine is going to be running out of CPU in 2 weeks' time. it's just it's a report that we can take and into our roadmap and our planning, so that we know where we need to focus in the coming milestones. And yeah, that's how we use it for capacity planning. So this was just something I was playing around with. If we wanted to get better predictions, we could take the data out of Prometheus and put it into something like NumPy and do Monte Carlo simulations, but really, like, that is totally overkill for what we're doing. What we've got is already providing us with quite a lot of value. So some final points. What we're trying to build here is a warning system, and it's designed to alert us to potential issues, and it ranks those by severity. So the most severe come up at the top, and then we can look from there. And this is it helps us to prioritize work in our system. And it's early days, but this method is actually giving us a lot of insight into what we need to work on and where we have resource saturation problems upcoming. So, of course, GitLab is open. So if you're interested in finding out more, I've just included like links to all of our metrics and alerts and some good Graphonet examples, although they're pretty big, and so yeah, might be a bit daunting. And obviously the obligatory we're hiring link. Thank you.
Thank you. We have the first question.
Yeah, a very short question. I don't see a link for slackline thingy.
Oh, if you just Google GitLab slackline, I'll warn you in advance. It was written as a Google Cloud Function at a time when Google Cloud Functions only supported Node, and I'd really like to rewrite it in Go, but it's a Node project. So, but if you just Google GitLab slackline, it's there.
So I had a couple questions. I'll start with just one though. When you talk about this capacity, a lot of those are defined on the instance type or whatever. Do you actually have to, in your alert rules, do you have to hard, some of them are easy, but if you think about even memory or
Yeah.
more complicated burstable IO,
Yeah.
do you have to hard code them, or do you have a way to a way to look up, given the instance size, to map that to another thing which tells you information about it?
So the only ones, a very good question. The only ones that we've got hard coded that I can think of right now are the write throughput and IOPS for our instances. And so I tried to take, Google presents a formula, and I tried to take that formula and turn it into PromCon, and it was, I failed. And so I just took the value and I plugged it in. So those are hard coded.
But I guess I mean like if you increase the instance types on which Redis runs, and now you have more memory available.
Yeah. So then, so we always, the bottom half of the quotient is always is nearly always comes from Prometheus as well. So it'll automatically expand, right? So if you have, I think I might be misunderstanding your question, but for memory, the bottom half of the memory thing is like the total memory on the node, for example. Gotcha. We also have one for C groups where it's obviously just the memory allocated to the C group, for example. But the only ones that are hard coded are the IOPS for the disks, because we can't calculate that.
Cool.
Question?
Oh, another one right here. So capacity planning always reminds me of like going to the dentist, where you should do it, but you don't normally go unless you have like a toothache or something.
Yeah.
And there's always like some fire you need to put out.
Yeah.
Did you have a hard time convincing your colleagues that this is worth doing? Because it obviously was a lot of work. Was that a hurdle at all?
I think the thing is that we had several situations where we had this like slow growth, and we were totally caught out by it. And then obviously everyone is fighting those fires. And so like it just felt like we could maybe put out some of those fires by getting that warning. And so it wasn't that much work. I guess I did most of it on my own, so I didn't have to convince people too much. But the thing is, at the same time, I'm quite not responsible, but I'm partially responsible for sort of helping with that roadmap of what we need to do next. And so the responsibility of saying like, hey, we need to look at this, we need to look at that, lies on me. So I built the tool so that I could do my job better. Yeah, exactly.
All right, one here. So those recording rules look pretty expensive. 1 week or 1 week data, and you crunching them. Did it affect your normal Prometheus operation?
Not as far as I know. Ben at the back might have a different opinion on that. Remember that it's not a lot of series that we're talking about. It's only the 200 or so.
Yeah.
But so the first thing is fairly limited number of series. The second thing is I only run it every 5 minutes because there's no, I could actually even run it less frequently than that. And I actually suspect because we hardly ever look at those rules, maybe I look at it once or twice a week, I could probably implement the whole thing now with subqueries and sort of just pay that price when I want to look at the dashboard rather than, real time.
Got it. Thanks.
Yeah.
Any more? Over there? Okay. You, and then we are done. Okay. Yep.
Thank you. The technique of rolling up saturation using max.
Yes.
That seems magical to me. I'm just wondering, is that like a really well-known technique? Did you make it up yourself? Did you read it in a paper?
I made that up, but I did make it up myself. So what often happens with it is that because you're just looking at the worst case, there's always a step when you see that something is saturated. You have to then go to another dashboard and resolve what it is that's saturated. So yesterday, we started getting a whole bunch of alerts about disk space on our primary Postgres instance was about to run out. And if you looked at the saturation graph for disk usage, it just was like a 45-degree angle over like an hour. And obviously that was kind of worrying. And then when we looked at it, it was actually the log partition, and that was the problem. So there's always that second step of then going. But I find that if we didn't use that and we kept all of those metrics, it'd just be too much data. And yeah, does that answer your question?
Did you encounter metrics where the standard deviation was too high to use this formula? And if so, how did you tackle those?
So a very good question as well. Absolutely. Like the other problem that we have is that sometimes what will happen is you have an incident maybe a few days before, and something spikes up from 15% to 100% and then goes back down. And that totally ruins your standard deviation, right? Because then it's for the next week, it's all out. But the thing is that because there's a human sort of taking that data and interpolating it before the next step, I'll take that into account and take a look. So it's not ideal. Like if we could have some sort of weighted average, that might be a better way to do that. But yeah, that is a problem with it. Yeah. Cool.
All right. Thank you very much.
Thanks. Cool.